A computer operating without instructions is an incredibly volatile machine. Raw electrical signals and data pulses fire across a circuit board billions of times a second, completely devoid of organization. At the physical level, we are dealing with components that process information blindly. The CPU cycles continuously, ready to execute any command, while the main memory blindly accepts data into whatever physical sector is available. In a modern computing environment, dozens of user applications are running simultaneously. Web browsers, text editors, and background processes are constantly competing to use these exact same finite physical resources at the exact same time. If a single application tried to directly control the hardware to save a file, it would have no awareness of the other programs. It would likely overwrite another application's memory sector, corrupting the data and triggering an immediate system crash.
To prevent this, every computer requires a central managing authority. We call this the operating system. It acts as the mandatory referee that sits exactly between the physical hardware and the software applications. Its core purpose is to transform a dangerous, unpredictable physical environment into a stable, standardized platform. By controlling who gets access to what, it allows software to run safely. This diagram maps out the hierarchy of a computer system. At the very bottom, we establish the physical hardware bedrock, the processors, memory, and devices we just discussed. The operating system forms the immediate layer wrapping directly over that hardware. It takes absolute ownership of the physical components. Capping the top of the OS layer is a thick boundary known as the system calls interface. This acts as a protective ceiling, sealing off the core operating system from the outside world. Resting directly on top of the system calls layer are the user interfaces. This includes your command line, graphical desktop environments, and batch processors. Finally, at the very top of the stack, we place the user applications themselves. This structural layout is known as the abstraction stack. It physically isolates end users and their applications from the raw hardware below, maintaining a mandatory buffer zone that keeps the system stable. Inside that central operating system layer, the OS justifies its entire existence by providing 5 specific non-negotiable services to the applications sitting above it. Service 1 is program execution. The OS must be able to load a program into memory, run it, and safely end its execution when finished, or abort it if it freezes. Service 2 handles I/O operations. Anytime a program needs to interact with an input or output device, like a keyboard, a monitor, or a printer, the OS manages the connection. Service 3 is file system manipulation. The OS dictates how data is organized into files and directories, handling all reading, writing, creating, deleting, and permission management. Service 4 provides communications. When different software processes need to exchange information, the OS routes packets between them, using shared memory or direct message passing. Service 5 is error detection. The OS constantly monitors the CPU, the memory hardware, and the user code for faults, taking immediate action to prevent a global system failure. While your computer has hundreds of system programs running in the background, like compilers and text editors, these 5 core services define the true operational baseline. Without these 5 bundled services, every software developer would have to write custom code to communicate with every single piece of physical hardware on Earth, just to save a simple text file. To enforce this structure, the computer physically divides its operations into 2 states: user mode, where everyday applications run, and kernel mode, the restricted zone where the OS and its 5 core services operate. User applications run with heavily restricted privileges. A web browser or a video game absolutely cannot access the 5 core kernel services directly. Instead, applications must ask for help. They do this using an API, or Application Programming Interface. Think of the API as a standardized language of requests. Different operating systems rely on different standard APIs. Windows uses the Win32 API. Unix and macOS rely on the POSIX API. Applications running in a Java virtual machine use the Java API.
When an app makes an API request, that request hits the system call interface. This interface is the literal gatekeeper between user mode and kernel mode. The software programmer only needs to know the high-level API command. The OS hides the complex, low-level implementation details completely out of sight. The system call interface acts as a strict security checkpoint. By forcing all requests through this bottleneck, the OS prevents malicious or broken user code from bypassing the API and hijacking the hardware. This diagram illustrates the precise journey of a single system call. Here, a user application simply asks to open a file, triggering an Open API command. The request travels down and hits the system call interface. This triggers an immediate mode switch, shifting the computer's processor from user mode into the highly privileged kernel mode. The interface takes the open request and looks up its corresponding ID number in an internal system call table. Armed with the correct ID, the OS now executes the actual kernel-level code required for the open operation, safely accessing the physical hard drive. Once the action is complete, the return journey begins. The kernel packages the status value, hands it back to the interface, and the processor switches back to user mode. The extra parameters required for these calls, like the specific name of the file, can be passed rapidly via the CPU's registers, stored in dedicated blocks of memory, or pushed directly onto the program stack. In a fraction of a millisecond, the OS bridged two entirely separated worlds, securely fetched a physical resource, and handed it back without the user application ever directly touching the hardware. This visualization shows the layered approach to operating systems. The system is designed as concentric rings, strictly moving from the hardware at the center outward to the user interface on the edge. Strict modularity means each layer only interacts with the one directly below it. This makes the system very easy to debug, but forcing data to pass through multiple rigid layers is slow and highly inefficient. Compare that to this diagram showing the monolithic structure used by traditional Unix. Here, all system services run crammed together in a single, massive kernel space. Monolithic systems are incredibly fast. Because all components share the same memory space, they don't need to waste time passing messages back and forth. But the monolithic design carries a critical flaw: immense complexity and severe vulnerability. Because everything shares the highest privilege level, a single bug in a monolithic device driver can trigger a fatal error that brings down the entire operating system. Packing all 5 vital services into one unrestricted kernel space maximizes raw performance, but it creates a massive single point of failure. Developers created the microkernel structure. Here, the kernel is stripped to its bare essentials. Bulky services like file systems are ejected entirely, forced up into user space. Because they no longer share memory, these modules must communicate with the core strictly through message passing. This creates a clear trade-off. The microkernel is highly secure and crash-resistant. If a driver fails, it doesn't crash the system. However, the constant overhead of passing messages significantly hurts processing speed. Because neither extreme is perfect, modern operating systems like macOS and Windows operate as hybrids. They mix the raw speed of a monolithic core with the stability of microkernel subsystems where it counts. Let's review the architecture. The computer exists as a 4-layer abstraction stack: hardware at the base, the kernel above it, the system calls boundary, and user applications at the top. Inside the kernel, the OS provides 5 key services: program execution, I/O operations, file systems, communications, and error detection. User applications can never touch these services directly. They must use an API, passing requests through the system calls interface to securely bridge the gap. And structurally, engineers must balance performance against stability. Monolithic kernels are fast but vulnerable, while microkernels are minimal and highly secure. Every tap, click, or keystroke executed by a user relies entirely on this invisible, highly structured hierarchy. It is the only thing keeping modern computing from descending into physical chaos.